Hello friends, welcome to my channel Emulation Nerd, and today in this module of algorithms, today we will be discussing about divide and conquer algorithm. So divide and conquer algorithm is the second most algorithm after the greedy algorithm, but it is one of the important algorithms that are being asked in technical interviews of tech giants, what we call FANG companies, Facebook, Amazon, Netflix, and Google, as well as other companies as well. So it's a bit common in interviews. So let's dive in. The general technique we use in divide and conquer algorithm is that we break the problem down into a set of non-overlapping subproblems. So it is important that subproblems that we generate to be of the same type as original. As you If you guys remember, we discussed about generating subproblems in greedy algorithm. So you might be considering what is the difference between the subproblems in greedy algorithm and in the divide and conquer algorithm. So if you guys haven't been through that video about greedy algorithm, I will be stating the link to that video in the description below. Now let's talking about the difference between the subproblems in greedy algorithm as well as divide and conquer algorithm. So in greedy algorithm, the subproblem needs to be of different type, or you can say that the subproblems need not be of the same type, to be more specific. And but in divide and conquer algorithm, the subproblems that we generate need to be of the same type. So the technique we use in subproblem is that we divide the given problem into subproblems, or to be very generic, let's give you an example of that. Suppose we are given an array A starting from index 1 to an. So if we need to solve it through divide and conquer algorithm, we need to divide it into two or more subproblems. I am giving you the more generic aspect of divide and conquer algorithm. So let's just divide it into the two parts, a1 to a n by 2, and the other part being a n by 2 plus 1 extending to a n, and it goes on dividing in this way until it get reduces to the most elementary part, what we call as a1 and a2. In this way, each of the element of the array will get reduced to only one element in the sub-array. So this is the generic explanation of what a divide and conquer algorithm looks like. So now let's look into a problem regarding divide and conquer algorithm. You guys might have heard of polynomial multiplication. Let me give you an example through that. Walk you through an example of that. So consider the polynomial multiplication. So a polynomial multiplication, for example, you can consider it as given an equation A of type x it looks something like 3x square 2x plus 5. So let's see the problem statement related to the polynomial multiplication. So according to the problem statement, we are given two n minus 1 degree polynomials. By the way, the polynomial stated here has degree 2 in the example. This has degree 2. So we are given two n minus 1 degree polynomials and the output should be the product polynomials. Let me give you a brief introduction. So for the input 2 n minus 1 d3 polynomial consider it as a n minus 1 x to the power n minus 1 plus a n minus 2 x to the power n minus 2, and it goes in this way till a1 x plus a naught. Similarly, this will be in the same format for b n minus 1 x n minus 1, and it will go till the same b naught, and the desired output would be the product polynomial. So the product polynomial might look somewhat like c 2n minus 2 x to the power 2n minus 2 plus c 2n minus 3 x to the power 2n minus 3, and it goes to c1x plus c naught. So where c2n minus 2 refers to a n minus 1 times b n minus 1, and it goes on like this. So it's got two terms to multiply together. The c2n minus 4 term would be three terms that multiply together, and we have more and more terms that get multiplied and summed together, and then fewer and fewer back down. So c2 then becomes a2 b naught plus a1 b1 plus a naught b2, and c1 becomes a1 b naught plus b naught a1, and c naught becomes a naught b naught. So the c we are seeing here in the output polynomial is just the permutation and combination. So it's the combination of permutation and combination we might have heard of during the mathematics lectures, mathematics days. So now stating some example input given to us would be n is equals to 3. A will have the coefficients with the values 5, 2 and 5 respectively, and B will have the values 5, 1 and 2 respectively. So the equation A and B will look something like this. To make it clear to you, I'm just writing the formal equation what it looks like. 5 being the coefficient and x to the power, since n is equal to 3, so it will be 2x plus 5, and equation B will look like 5x square plus x plus 2, and we need to give the output coefficient of the product polynomial. So the product will look something like ax bx equals 15x square, sorry, x to the power 4, since the first square or the since it is of degree 3, so first both x to the power 2's will get added, and after that 13x cube (33x square) 9x plus 10. So this will look like the product of equation A and B, and the output desired would be output desired would be 15, 13, 33, 9, 10 respectively in this order, as the coefficients are in this order only. So now looking into this problem, we first look into the naive algorithm we can think of. So the naive algorithm basically just says, well, first off, let's create a product array. This is basically opening to be the C, or going to be the C, the result, and it's going to be the highest degree 2 into 2 times n minus 2. So it's going to have 2 times n minus 1 terms all the way from the 0 term up to the 2 times n minus 2 term. So we will initialize it with 0, and then we have a nested for loop, and at every time what we will do is we will calculate a particular pair. So this is the naive algorithm that we can simply think of for this problem, and I will just write down the algorithm what I thought of, or the naive algorithm what I thought of for this problem. So let's see. So we can name the function as multiply poly with a, b, and n provided to this function. So we can initialize product array as array 2n minus 1, and we will run a for loop for I from 0 to 2n minus 2. Since there will be 2n minus 2 indices in this array, so we need to iterate for each of them, and the indices will run from 0 to 2n minus 1 inclusive of them. So product of I should be, or we should initialize it with 0. Now the first for loop will be for the initialization of the product, for I from 0 to n minus 1. So in this for loop we will be creating all the combinations that a particular index can have for j from 0 to n minus 1. And product I plus j equals product of I plus j plus of the combination which we just formed, that will be the product of ai times bj. And so after that we will just return the product. So this is the naive algorithm we can think of. And in the naive algorithm we can see that the runtime of this naive algorithm is n square. Big O of n square. Since we have two loops which we need to iterate in order for the generation of each combination, so the time complexity or the runtime would be big O of n square, which is not a good practice to have as a runtime in algorithms. So we can think of another divide and conquer algorithm. We will think about the naive approach for divide and conquer algorithm. So the idea is we are going to take our long polynomial and we are going to break it into two parts, the upper half and lower half. So let ax sorry be d1 x to the power n by 2 plus d naught x, where this d1x will be of a n minus 1 x n by 2 minus 1 plus till a n by 2, and this d naught x will look something like a n by 2 minus 1 x to the power n by 2 minus 1 plus up till a naught. So we have two parallel subproblems, the high and the low. We do the same thing for b. So the same thing for b, we will describe it as bx is equals to we denoted the previous one for a as d1x, so we will denote it as e1x x to the power n by 2 plus e naught x, and the e1x and e naught x will be the same in the same way as d1x and d naught x. So now when we do our multiplication, then we just multiply together d1x n by 2 plus d naught and e1x n by 2 plus e naught, and that yields 4 terms. So what it yields as ab equals d1 x n by 2 plus d naught times e1 x n by 2 plus e naught. So the resultant would be something like d1 e1 x to the power n by 2 plus d1 e naught plus d naught e1 x to the power n by 2 plus d naught e naught. I just noticed that by mistake I just introduced n by 2, so here it should be n, because n by 2 plus n by 2 in the power will result to n. So we got these three coefficients which we need as an output after the reduction by the name divide and conquer algorithm, and it results this 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 and these four combinations which we need to have. So these are all polynomials of degree n by 2. So now we can go ahead and use a recursive solution to solve this problem. So it gives a divide and conquer problem. Its runtime is, let's just calculate the runtime. Tn is equals to 4, since we are having 4 subproblems. 4 t n by 2, each of size n by 2. After the first division, on each division, each node is creating 4 subproblems. Dot four. Because we are breaking into 4 subproblems and each of them takes t n by 2, because the problem is broken into half. So let me just drive you through an example of this. Or yeah, ax will be something called 4x square plus 3x square plus 2x plus 1, and the bx provided would be something like x cube. Sorry, it should be x cube, since plus 2x square plus 3x plus 4, and d1x would look something like 4x plus 3, and d2x will look something like 2x plus 1. In the similar way, e1 x will look like x plus 2, and e0 x will look like 3x plus 4. And now as we need to compute this d1 e1 d1 e0 d0 e1 and d0 e0, so let's compute all of them. d1 e1 will result in 4x square plus 11x plus 6, and d1 e0 will result into 12x square plus 25x plus 12 in the same, and d not even will result into 2x square plus 5x plus 2, and at the last d naught e naught will result into 6x square plus 11x plus 4. So these are all the 4 combinations we need to generate, and after that we need to put it in this particular format, and then we will get our resultant product polynomial and hopefully the coefficient from there. So let me just write down the algorithm for this which I thought of. So function multiply 2 with a1 b1 and a1 b1 provided to it. So sorry, since I have used a and b for both the equations, I don't need to have 1 and 2 respectively. So capital A and capital B corresponds to the original equation provided to it, and small a and small b represents the index of capital A and capital B respectively. So let's move forward. let R be an array of size 0 to 2n minus 1, since it is going to store 2n minus 1 elements. So if n equal 1, r0 equals a0, a1 or a times capital B, and return R. Now since the number of elements are greater than 1, we need to compute for 0 to n minus 2, and for this we will use the recursive approach mul2 a b of size n by 2 with a and b being the indices, and for another part 0 to 2n minus 2 mul2 a b size n by 2 a plus n by 2 and b plus n by 2. We are adding n by 2 to the current indices because we are referencing to the right half of the division we just did. And we now calculate the combinations. We have d naught e1 equal to mul2 ab of size n by 2 a b plus n by 2, and d1 e naught will be mul2 a and b of size n by 2. Now the right part for the first equation and the left part for the second equation, as we refer to the left part of the first equation and the right part of the second equation in d naught e1. And now we will calculate the r from n by 2 n plus n by 2 minus 2, so plus equals d1 e naught plus d naught e1. And finally after this we should return the r computed here. So this is the recursive naive divide and conquer algorithm which we thought of with all the 4 combinations by reducing it to the 4 combinations. So after this, let's just validate our time complexity. So since we are dividing it into halves in each part, so it will be of tree structure. So let's just represented by level. In between we will draw the tree structure, and after that we need to have the number of nodes at each level and the work that needs to be done at each level. So at level 0 there will be one node of size n, so number of nodes will be 1, and the work will be k being some constant work, some addition multiplication at each step, and since it is of size n, the work should be directly proportional to n. At level 1, since we are dividing int into we are segregating every halves, so this level will have n by 2 n by 2, since we are computing 4 combinations in each step, so n by dividing them into halves, so n by 2 and n by 2. So number of nodes at this step would be 4, and the work will be 4 times k into n by 2, so it gets reduced to k times twice. So in this way, at any level I, it will have each node of size n by 2 to the power I. And number of nodes at this level would be something called 4 to the power I, since at every step we are generating 4 nodes, so at the level I the number of nodes would be 4 to the power I, and the work needs to be done here is somewhat like 4 to the power I k times n by 2 to the power I, and now as we see it will get reduced to k times 2 to the power I n, and this goes on till level log to the power to the base 2, log n with base 2. Since we are dividing it into a tree, so a tree can have a maximum depth of log n with base 2, and here we will have each node of size 1. So at this level we will be having something called log base 2, 4 to the power log n with base 2 number of nodes, and the work needs to be done here is something like 4 log base 2 n into k, and here the number of elements in each node is 1, so it is 1, so it gets reduced to k times n squared. Now you will be confused why it get reduced to k to the power n square, because 4 will get reduced to 2 to the power 2 log 2 n. So this is a property of log. So log 2n, so this is a property, so it will get reduced to something called 2 log 2 n square. So it will get reduced to n square. Now I think you guys might be clear why 4 to the power log n with base 2 get reduced to n square. Yeah, so let's just calculate the generic work that needs to be done, or total. Summation from 0 to log base 2 n with 4i k n by 2i. So we need to calculate total work that needs to be done, which will give us the generic time complexity. So in this case it will get reduced to somewhat theta n square. That means the average time complexity being the n square. So this n square time complexity and the naive approach which we thought of is also of the n square time complexity. So there is not much difference between the divide and conquer algorithm and the naive approach which we currently thought of. So we need to think of something much more in order to reduce the time complexity, as n square is not the acceptable time complexity in competitive programming as well as in coding interviews. So now let's think of something faster divide and conquer algorithm. So there is one approach called Karatsuba approach. So Karatsuba is a mathematician who theoretized that n square is the best way that one could do. So there was a lower bound of n square doing polynomial multiplication, and it needs 4 multiplications. As we can see, it needs 4 multiplication: d1, d0, e1, d1, e1, d0, e1, and d1, e0, and d0, e0, and they can be rearranged in order to get the resulting or the resulting multiplication polynomial. So Karatsuba approach that instead of 4 it can be reduced to 3 multiplication. So what he did there, for a x is equals to a1 x plus a naught and bx equals to b1 x plus b naught. So the resultant will be c1 x equals a1 b1 x square plus a1 b naught plus b naught a1 x plus a naught b naught. So it needs 4 multiplications, this one, this one, this one, and this one. So this can be rewritten as a1 b1 x plus a1 plus a naught times b1 plus b naught x plus a naught b naught. So where it needs 3 multiplication, a1 b1, a1 plus a naught times b1 plus b naught, and a naught b naught. So why it matters? Because we are reducing the number of problems at each level. Previously in the divide and conquer algorithm, we are reducing it to four sub problems, and in this approach we are reducing it to 3 sub problems. So let's just determine its time complexity in order to prove whether it is a better approach as compared to the previous naive divide and conquer algorithm. So let's level uh, with number of nodes as well as work. So at level 0, as usual, it should have a single node with n elements. So node 1 work k times n. At level 1 it gets reduced to n by 2 with 3 nodes. So here the number of nodes is 3 with k being 3 times k into n by 2, which results into 3 by 2 k n. Similarly, at some level I, it should have n by 2 to the power I elements in each node. And the number of nodes will be somewhat 3 to the power I, and the work that needs to be done would be 3 to the power I k times n by 2 to the power I. So it will now become k times 3 by 2 to the power I times n. Similarly, at the base level with the height log and with the base 2, it will have one element in each node. And the number of nodes here will be somewhat 3 to the power log base 2 n. So the number of work that needs to be done here is 3 to the power log n with base 2 times k times 1. So let's calculate the total work that is done here. Summation from 0 to log n with base 2, and the generic work is 3 to the power I times k n by 2i. So it will get reduced to somewhat theta n log base 2 with 3. You need to do some calculation as well as know some log series and the properties of logarithms in order to result into this, and the final it would be somewhat like n to the power 1.58. So in the previous two approaches which we saw, the time complexity were n square, and the current approach which we had, the time complexity get reduced to n to the power 1.5h, which is relatively better than n square. So let's code it. So this is a better approach you need to consider while solving this polynomial problem which we discussed right now. So this is all about divide and conquer algorithm, how it works. If you have any confusion or have any such questions regarding divide and conquer algorithm, please do comment down in the comment box, and I will surely make a separate video or try to clarify the confusion or thoughts anyhow I can. So this is all from divide and conquer algorithms in algorithms module. So please do like, comment, share and subscribe, as well as press the bell icon so that you don't miss any video. So let's meet in the next video then. Bye. Goodbye.